Website fingerprinting (WF) attacks identify visited websites over anonymized connections by analyzing patterns in network traffic flows. The modern internet environment has introduced growing complexity and variability, while the limited adoption of privacy-enhancing technologies like Tor necessitates a re-examination of WF approaches. This study addresses four main limitations of prior WF methods. First, the focus shifts from identifying specific web pages to classifying entire domains of a website, including traffic from advertisements, images, subpages, and single-page applications. This approach acknowledges the diversity of modern web traffic. Second, the study employs a deep learning model called WFNet, which leverages convolutional neural networks, CNNs, to identify a destination website using packet size, jitter, or both. This method eliminates the need for heuristics to find page boundaries, making eavesdropper attack models more realistic. Third, the research highlights the importance of training traffic quality, demonstrating that classification accuracy can be significantly reduced when the training data lacks variability in network location, performance, and client's computational capability. To enhance the base CNN's efficacy, the study employs domain adaptation, allowing it to discount irrelevant features such as network location. This approach improves the model's robustness to varying network conditions. Lastly, the paper evaluates several defensive strategies against seamless WF attacks, emphasizing the need for more realistic and comprehensive WF attacks and defenses. The study notes that most users opt for standard protocols like HTTPS, VPNs, DNS over TLS, and DNS over HTTPS instead of privacy-enhancing technologies like Tor due to performance issues and low adoption rates. This highlights the importance of developing more effective and user-friendly privacy-enhancing technologies to mitigate WF attacks. The authors address three primary limitations in traditional website fingerprinting (WF) attacks. Firstly, they note that previous works often focus on individual page URLs or classify sites using a single homepage, which may not accurately represent real-world scenarios. Secondly, page size is a significant feature in WF attacks, but in practice, an attacker may struggle to split a TCP stream at page boundaries. The authors demonstrate that up to 30% accuracy can be achieved by utilizing web page size alone as a defining feature. Thirdly, many prior works lack experiment environments that are representative of real-world network conditions. To address this, the authors collect traffic from different network environments, including cloud data centers, university networks, and home-based networks, to demonstrate the impact of network conditions on WF accuracy. They also emphasize the importance of the client's computing environment, such as processor speed and available memory, on traffic patterns. The authors propose a more realistic attack model, where the attacker only needs to observe 500 contiguous packets anywhere over the entire session, without regard to timing or boundaries. This seamless WF attack model is more practical and relaxed than traditional models. In their experiments, the authors use synthetic traffic in a closed-world approach, assuming the user's traffic is one of the sites in the training set. They evaluate the performance of their WFNet model and compare it with three mainstream WF attack models, achieving accuracy rates exceeding 90%. The authors stress the importance of having a comprehensive and diverse training set, including multiple network environments and computational environments, to achieve high accuracy. They also explore the use of domain adaptation to maintain accuracy when training traffic is acquired at different network points from the training and testing sets. This approach helps retain features related to website classification while eliminating features related to locations, improving the model's generalization across different locations. Finally, the authors discuss the exploration of two privacy-enhancing techniques using evasion techniques, which involve altering the input to a WF attack model to mislead it. This research paper delves into the application of deep learning techniques in website fingerprinting attacks, focusing on enhancing accuracy and efficiency. It discusses various approaches to traffic classification, including traditional classifiers such as support vector machines, nearest neighbor clustering methods, and neural networks. The study also highlights the limitations of existing website fingerprinting methods, which primarily rely on monitoring and analyzing the timing and size characteristics of network traffic. The authors present a new method for website fingerprinting using a deep learning model called WFNet, which utilizes convolutional neural networks, CNNs, and recurrent neural networks, RNNs, to classify websites based on their network traffic. They compare their approach with other state-of-the-art models, including the Moore classifier, Lopez classifier, Williams's model, and Old's Bayesian neural networks. In addition to discussing the background and related work, the paper outlines two methods for obscuring the destination website by modifying packet timings or adding additional dummy packets. These methods, known as inflation and active injection, aim to reduce the accuracy of WFNet in identifying websites. The paper also summarizes information from figures, tables, and graphs efficiently, providing insights into the performance of WFNet under different conditions. The study concludes by summarizing its findings and speculating on what it would take to make networking protocols privacy robust in the face of machine learning techniques. It emphasizes the potential of machine learning in web application classification, particularly in the context of website fingerprinting. A comprehensive analysis of network characteristics across various locations reveals significant variations in average interpacket interval, packet size, and browser bandwidth, emphasizing the need for adaptable models. The neural network structure implementing domain adaptation, as illustrated in Figure 2, is crucial for mitigating domain shifts. A comparison of the author's dataset with traditional datasets, presented in Table 3, showcases the diversity and scale of their dataset, which includes data from multiple environments and a significantly higher number of unique URLs per website. The authors provide background on three machine learning techniques relevant to their work: transfer learning, domain adaptation, and backdoor learning. Transfer learning leverages knowledge learned from one domain to improve performance in another related domain, using the pre-train fine-tune paradigm to effectively tackle diversity and complexity. Domain adaptation addresses disparities in data distributions across different domains, with the incorporation of domain indices proving helpful in balancing differences among domains. Certain models can smoothly transition between domains during continuous domain shifts, enabling better adaptation to the target domain. Backdoor learning focuses on understanding and mitigating vulnerabilities associated with manipulated machine learning models, aiming to produce error-ridden outputs that compromise model performance. The author's dataset and proposed methods are designed to tackle the complexities of website fingerprinting attacks, leveraging transfer learning, domain adaptation, and addressing potential vulnerabilities through backdoor learning to develop a robust model that can effectively identify websites amidst encrypted traffic. The author's work builds upon previous research in the field, including the method proposed by Panchenko et al. 30, which utilizes support vector machines, SVM, to achieve high recognition rates in complex network environments. The author's approach aims to enhance the performance and generalization capabilities of their WFNet model by leveraging transfer learning and domain adaptation. The discussion of potential vulnerabilities associated with backdoor learning highlights the importance of addressing these concerns in future research, with significant implications for the field of website fingerprinting attacks and machine learning. Traditional website fingerprinting, WF, is limited by 9 key assumptions, including closed-world modeling, sequential browsing, and isolated traffic, which restrict its applicability in real-world scenarios. These limitations are addressed by seamless WF, an open-world modeling approach that acknowledges users may access sites beyond the monitored scope. This paradigm shift significantly impacts classifier selection and classification accuracy. The paper presents a threat model for seamless WF, incorporating backdoor learning approaches to enhance privacy by altering traffic patterns and reducing trained model accuracy. The study's focus is on the robustness of various protocols against fingerprinting attacks, moving beyond Tor traffic. A new dataset, a WF775, is introduced, comprising 775 websites with varying traffic volumes and padding zeros. Figure 4 illustrates the dataset's distribution, showcasing the mean number of padding zeros and standard deviation across each class. Furthermore, WFNet Base, a neural network architecture designed for WF tasks, is presented. Its structure is depicted in Figure 3. The effectiveness of WF-net base in different environments is demonstrated in Table IV, which presents its accuracy when trained on one location and tested on another. By introducing seamless WF, AWF 775, and WF-net base, this research provides a novel approach to WF, addressing the limitations of traditional methods and enhancing the robustness of WF tasks in real-world scenarios. Website fingerprinting research has traditionally relied on homepages as representative samples, assuming high accuracy rates in closed-world settings. However, this approach fails to capture the diverse content styles within a website's pages, inadequately reflecting its traffic patterns. To address this limitation, a novel evaluation methodology is proposed, where a comprehensive representation of a website is obtained by visiting most or all of its subpages. This approach is demonstrated using a dataset of over 20,000 unique subpages per website, providing a more realistic assessment of website fingerprinting's effectiveness in real-world conditions. Realistic browsing behaviors are also crucial, as modern browsers and technologies have shifted from discrete page interactions to continuous user engagement. To capture these complexities, Puppeteer is utilized to simulate a wider range of user actions. Previous datasets are criticized for their unrealistic observability, where complete packet sequences are processed into single-page packet sequences in a laboratory setting, often padded with zeros to uniform lengths. This padding introduces additional distinguishing features that significantly aid classification but may not accurately represent real-world scenarios. Moreover, using page size as a feature can be misleading, as it can be artificially inflated by padding zeros. The importance of considering differences in network and computing environments is also highlighted, including physical location, ISP providers, and client capability, which can greatly influence traffic features. A comparison with prior works in Table 3 demonstrates the need for a more comprehensive and realistic evaluation methodology for website fingerprinting attacks. This novel approach provides a more accurate representation of website fingerprinting's effectiveness in real-world conditions, addressing the limitations of traditional evaluation methodologies. Website fingerprinting poses a significant challenge, particularly in Tor networks, where existing approaches have limitations. This study emphasizes the importance of collecting more traffic to improve per-site accuracy, diverging from previous works that focused on expanding the number of sites. The innovative approach of Cherubin, which leverages information exposed through DNS queries, faces challenges with the emergence of encryption protocols like DNS over HTTPS, DO, and packet distribution variability across environments. To address these challenges, a new threat model is proposed, assuming that classification can be achieved with fewer packets, 500 fixed-length packets, and allowing attackers to initiate monitoring at any time without additional noise and latency associated with identifying web page boundaries. This model considers frequent user interactions, subpages, page advertisements, and other elements as representations of the website's traffic. The methodology involves synthetic trace generation, similar to prior works. A browser is used to access a set of known websites, and recorded packet traces are processed into feature vectors to train a WF-net. The website corpus consists of 42 websites, with 20 websites collected in 8 different environments, selected based on popularity and similarity. To generate more representative traces, Puppeteer, a library to remotely control a browser, is employed. All links within each website are extracted, filtered, and assembled into a pool of web pages. Different weights are attributed to the pages based on their occurrence frequency, and random sampling is used to select the next page for navigation. This process is iteratively repeated until sufficient data is acquired. Machine learning model input features are extracted from packet arrival time and size, stored as 32-bit floating-point numbers within an array. The model structure is altered to support domain adaptation, and a pre-training and fine-tuning approach is employed. The dataset composition is illustrated in Table V, highlighting the 42 websites from which browsing data was collected in a university setting. The authors acknowledge the limitations of their approach, including potential variability in packet distribution across different environments and the emergence of encryption protocols like DNS over HTTPS, DO. This section of the research paper focuses on the collection of network traffic data for website fingerprinting analysis. Data was collected from various environments, including a university, cloud services, and cable home setups. A total of 25 popular websites were used to gather traffic data, resulting in 10 million packets and 20,000 input vectors. The university environment utilized two Dell R7525 computers with high-speed connections and powerful processors, while cloud services were provided by 3 different providers in 5 cities across 3 countries. Cable home setups consisted of 2 Hewlett-Packard PCs with varying CPU performances and network bandwidths. The paper also introduces WF-NetBase, a CNN-based model designed to classify websites based on their network traffic patterns. WF-NetBase features 17 convolutional layers connected to 3 fully connected layers, with batch normalization applied after each convolutional layer to enhance adaptability. The model's structure includes 5 residual blocks, each employing a residual connection strategy to improve stability and convergence. This design led to a 93% accuracy in website classification with 2 million samples. An expanded version of WF-NetBase, named WF-NetLarge, was also developed. This model features 6 additional convolutional layers and increased channel numbers in each layer, resulting in over 20 million parameters. The performance of WF-NetBase and WF-NetLarge is compared in the mix location task, with WF-NetBase achieving higher accuracy in this task. In Table V, the accuracy of various mainstream website fingerprinting (WF) attack models within a closed-world seamless WF environment is presented. The proposed WF-NetBase and WF-NetLarge models outperform other models, achieving high accuracy rates of 0.92 and 0.94, respectively. The paper then discusses the challenge of domain adaptation in WF attacks. A deep learning model trained on data from one ISP location typically achieves low accuracy when tested on data from another location. To address this issue, the authors propose a domain adaptation strategy that enables the model to learn alignments of data streams across various scenarios and account for different network and client performance. The authors consider data collected from different cloud servers as distinct domains and aim to extract domain invariant features between the source domain and the target domain. They utilize the WF-NetBase model as a feature extractor and employed 2 separate fully connected networks as website classifiers and domain classifiers. The domain classifier takes encoding from both the source and target domains and tries to distinguish between them. A gradient reverse layer is introduced at the beginning of the domain classifier to min-max the loss function. The loss function is defined as min w, f max dlf, w, f, minus lambda dld, d, f, where lf, w, f, denotes the loss of the feature extractor, ld, d, f, denotes the loss of the website classifier, and lambda is a hyperparameter that balances the 2 loss functions. The goal is to minimize the label classifier loss while maximizing the domain classifier loss, thereby extracting shared features between the target domain and the source domain. The website classifier is trained using source data with labeled website categories, and the domain classifier is trained using domain IDs assigned to the source and target domains. This domain adaptation training does not require any labeled target domain data, making it possible to reuse the attack model on various servers and user terminals. To address the issue of integrating datasets from various scenarios, the authors propose assigning distinct indices to each dataset within a scenario and tasking the domain classifier with predicting these indices. This approach enhances the feature extractor's ability to capture common features across diverse scenarios. The paper also discusses the pre-training and fine-tuning of the WF-NetLarge model. The model is trained on datasets originating from diverse locations, and the parameters of the earlier convolutional layers are frozen while the parameters of the fully connected layers are fine-tuned using a relatively small amount of data. The evaluation section presents 3 attack scenarios, and the WF-Net model is used as the foundational attack model to demonstrate its accuracy across these scenarios. The impact of increasing the number of websites and the number of packets is also investigated. Overall, the paper proposes a novel domain adaptation strategy for WF attacks, which enables the model to learn alignments of data streams across various scenarios and account for different network and client performance. The proposed WF-net models achieve high accuracy rates and demonstrate the effectiveness of the domain adaptation strategy. The authors present the results of seamless website fingerprint attacks in various environments, focusing on the precision of attacks within a specific location. Figure 5 displays the accuracy of training on one location and testing on that location, with each location comprising 22 websites. The results show that the proposed WF-net model achieves high accuracy in all locations, with precision varying across different websites. The authors also investigate the effect of training on multiple locations and testing on an unfamiliar location, with and without domain adaptation. The results are presented in Figure 6, demonstrating the effectiveness of domain adaptation in improving accuracy. The experimental setup is replicated across 8 distinct datasets, using half of the data for training and the remaining for validation and testing. The validation set is used to gauge training accuracy, while the testing set assesses the WF-net performance post-training. The authors define precision as the true positive rate, representing the proportion of correct website identifications among all positive identifications. Accuracy, on the other hand, represents the overall rate of correct predictions. The average accuracy is conveyed through a red dashed line, indicating the cumulative performance across all websites. The results of individual websites are visually represented through bar graphs, with overall accuracy indicated by a red dashed line. Each website has a unique fingerprint, and the WF-net model is able to capture these site-specific features. The section concludes by discussing the implications of the results and the potential for future work, including the evaluation of enhancements to Scenario C attacks and the exploration of feasible defense mechanisms against seamless website fingerprint attacks. Evaluating website fingerprinting attack models in a closed-world task within a university dataset reveals significant limitations in conventional approaches. The QML and DLWF models, leveraging SVM classification and a basic deep learning framework, respectively, achieve accuracy rates below 30% for classifying 10 websites. In contrast, the triplet fingerprint algorithm achieves a 75% accuracy rate, but this declines significantly when the number of websites increases to 20, indicating a lack of stability and generalization capabilities. To address these limitations, deeper CNN models, specifically WF-net base and WF-net large, were employed, significantly enhancing stability and achieving over 90% accuracy in both 10 and 20 classification tasks without a noticeable decline in accuracy as the number of labels increased. The applicability of this attack strategy across different network environments was also assessed. With a substantial training dataset, the model consistently achieves an accuracy rate above 90% across all datasets, highlighting the potential for accurate attacks when attackers possess detailed knowledge of the victim's network settings. The precision for each website using all traffic sets for both training and testing is presented, with the model achieving an overall accuracy of 95%, and only one website, The New York Times, recording a precision below 90%. This suggests that, with sufficient preliminary training data, attackers could develop a model with robust generalization capabilities, enabling seamless attacks on victims across multiple scenarios. The distinct contributions of different environments and the implications of collecting training data in one environment and applying it to another were also examined, which is crucial for understanding the potential risks associated with website fingerprinting attacks and developing effective countermeasures. In novel environments where attackers cannot pinpoint the victim's specific browsing context, the generalization capabilities of attack models are explored. The analysis reveals that training and validation data from one location significantly impact accuracy when testing data is sourced from another location. Classification accuracies across various training and testing environment pairings are presented in Table IV, showing high accuracy along the diagonal where training and testing environments match, but substantial accuracy declines off diagonal, highlighting challenges in cross-environment generalization. Diversifying training data bolsters the model's ability to generalize beyond a single training context, but the gains in performance are somewhat muted. In unfamiliar settings, the model's accuracy declines, such as directly targeting users in a university setting, where accuracy halves to just 50%. The number of websites is a key factor, with Table 8 showing stable accuracy as the number of websites increases from 10 to 40, stabilizing at about 91%. The quantity of samples utilized for training is also pivotal, with Table 7 demonstrating that once the count of vectors per site surpasses approximately 50,000, accuracy plateaus at a mid-90% range. The analysis also examines the impact of aged traffic on the model's performance, with Table 8 showing that utilizing a training set that is 9 months old results in an accuracy decline of roughly 10 to 15 percentage points. However, the application of domain adaptation techniques moderates this drop in accuracy, maintaining it within a 5 to 8% margin. The results highlight the significant real-world challenges website fingerprint attacks face, underlining the substantial practical hurdles in applying these attacks across diverse network environments. The findings also demonstrate the importance of domain adaptation techniques in mitigating the impact of temporal changes on the model's performance. The limitations of this study include the assumption that attackers cannot pinpoint the victim-specific browsing context, which may not always be the case in real-world scenarios. Additionally, the analysis focuses on a specific type of attack, website fingerprinting, and may not generalize to other types of attacks. Future work could involve exploring the application of domain adaptation techniques to other types of attacks, as well as investigating the impact of other factors, such as network topology and user behavior, on the model's performance. Attackers seeking to enhance their model's effectiveness in unfamiliar environments may employ two strategies. The first involves fine-tuning existing attack models with sparse labeled data from the target environment, achieving substantial levels of attack precision in significantly reduced timeframes. This approach leverages the limited available data to adapt the model to the new environment, resulting in improved performance. The second strategy utilizes domain adaptation algorithms to negate the effects of varying environments or timings, resulting in improved average precision and accuracy. This approach enables the model to generalize across different environments, reducing the impact of environmental changes on its performance. The authors also investigate the accuracy of using only packet jitter or packet size as features for classification. Their findings indicate that using either feature alone results in a slight decrease in average accuracy, suggesting that both features capture significant aspects of the website's inherent structure. To improve privacy protection, the authors proposed two evasion techniques that introduce randomization to contaminate traffic features. Inflation involves adding a randomized extra delay to packet jitter or padding packets with random amounts of bytes, while active injection entails injecting a randomized set of extra packets into the data stream. These techniques aim to disrupt data interception or analysis attempts based on predictable transmission patterns, thereby enhancing data transmission security and bolstering resistance against privacy infringements. The proposed evasion techniques can be used to protect against attacks that rely on predictable transmission patterns, such as those employing machine learning models. By introducing randomization into the data stream, these techniques can make it more difficult for attackers to intercept or analyze the data, thereby improving privacy protection. Figure 9 presents the efficacy of evasion techniques, specifically inflation and active injection, in reducing the accuracy of website predictions using machine learning models. Inflation involves adding random jitter and extra bytes to existing traffic, while active injection entails inserting fixed-sized packets into the packet stream. Both techniques significantly decrease machine learning model accuracy, thereby safeguarding user privacy. Inflation requires substantial jitter and byte additions, resulting in an average delay of 50x and a 50x increase in total data size, making it impractical for web browsing applications due to associated costs. In contrast, active injection is a more effective technique, reducing website identification accuracy to 6% by adding a trigger size of 35 packets. This approach only increases the excess average delay by 6% and the extra size of the traffic by 2%, making it a more feasible solution for real-world applications. The researchers experiment with varying trigger sizes, ranging from 2% to 10% of the original number of packets, and maintaining a constant size between 50,250 bytes per packet within a trigger. The results indicate that as the trigger size increases, machine learning models increasingly rely on triggers for website predictions, establishing a correlation between website labels and inserted triggers. Intentionally altering the inserted triggers substantially alters the machine learning model's label predictions, thereby protecting user privacy. The approach consistently reduces model accuracy to single digits, outperforming the direct addition of latency and size to existing packets. The evaluation results highlight the significance of trigger size and packet characteristics in the effectiveness of evasion techniques. The findings suggest that active injection is a more practical and effective approach for reducing machine learning model accuracy and safeguarding user privacy. The study's findings have significant implications for website fingerprinting and preserving privacy in the face of machine learning-based attacks. The results obtained for HTTP/3 over IPv6 are expected to be similar to those for HTTPs, TCP, indicating that identifiable patterns in website structure are likely to be visible in quick and derived protocols. Notably, the study reveals that website structures, such as the use of templates or the placement of advertisements, result in identifiable patterns at the TCP and IP level. These patterns can be exploited by attackers to fingerprint websites, compromising user privacy. To mitigate this risk, the authors propose creating copycat sites that mimic the structure of the original website but with different content. This approach could potentially provide additional privacy by making it more difficult for attackers to distinguish between the original and copycat sites. Furthermore, the authors suggest that clone sites could be used to better understand the relationship between website structure and traffic patterns, informing the development of more effective privacy-preserving strategies. The authors also propose a strategy for preserving privacy by allowing protocols to add randomized data in a manner that is not detectable by attackers. This approach could help to mask identifiable patterns in website structure, making it more difficult for attackers to fingerprint websites. Future work in this area could focus on developing and evaluating the effectiveness of this strategy, as well as exploring other methods for preserving privacy in the face of machine learning-based attacks. This page presents a comprehensive list of 48 research papers on quantum computing, focusing on various aspects such as quantum algorithms, quantum hardware, and quantum error correction. The compilation aims to provide an overview of the current state-of-the-art in quantum computing research. The first section delves into quantum algorithms, which are essential for leveraging the computational power of quantum systems. Papers in this section explore different types of quantum algorithms, including those based on Grover's algorithm, Shor's algorithm, and quantum Fourier transform. These algorithms have been shown to offer significant speedup over classical counterparts for specific problems. The second section discusses quantum hardware, emphasizing the development of practical quantum computers. It covers various quantum computing architectures, such as superconducting qubits, ion traps, and topological quantum computing. The papers also address the challenges of building scalable and reliable quantum hardware, including error rates, coherence times, and control over quantum gates. Quantum error correction is the focus of the third section. This is a critical area of research, as quantum information is highly susceptible to errors due to decoherence and other environmental factors. The papers in this section present various quantum error correcting codes, such as surface codes, Shor's code, and Steen's code, along with their performance and limitations. In conclusion, this page offers a broad perspective on the current advancements in quantum computing research, encompassing quantum algorithms, quantum hardware, and quantum error correction. It serves as a valuable resource for researchers and stakeholders seeking to understand the complexities and opportunities in this rapidly evolving field.